It'll be at Orange County Convention Center, October 26th to the 28th. Okay, at this time, I would like to introduce Tim.
Morning, everybody. She mentioned the continuing education credits for the little 5-question quiz. If you're when in doubt, think true. True. As she mentioned, Tim Skell, application engineer, work for ABB. My specialty is VFDs in the HVAC industry. About 2 years ago, we started a pretty big renovation at our facility and basically gutted out the entire HVAC system. And since we work in this industry, we wanted to use our building a bit as a showcase. So later on, you'll see a couple pictures. We have our mechanical room behind glass. I can take a white glove and go up to something and go like this, and it looks pretty darn clean. So when you see pictures later on, it's not quite your normal mechanical room, and we did that on purpose to use it as a showcase. So we've been bringing people into our building and using it as a training technique, and you can kind of see the light turn on when you start talk about certain topics, and we can see things and play with it and do hands-on. And since it's hard to get guys like you to come up to Wisconsin where I'm at, we figured we'd do our best to bring our building down to you to help educate you where we can on what we've done, how we used VFDs in our building, and along with how we use BACnet. Before we get started, just so I get an idea who's in the room, how many of you guys are facilities managers or technicians in charge of keeping your building up and running? Good portion. How many consulting engineers in here? Anybody in charge of energy saving projects? Okay. Anybody I missed? Who wants to pipe up? One. And what do you do?
I manage an IRS condo building.
Okay. Cool. We have a small enough group. As if you have a question on anything, please stop me, raise your hand. If I don't see it, just shout out. I'd much rather have a back and forth a little bit opposed to me just sit here and spewing information at you for the next 40 minutes. So I mentioned I'm in Wisconsin. Size of the building I'm going to be using as an example is just under 150,000 square foot. And before I forget, in the BACnet journal, there's one at everybody's chair here. There's an article on this building right here in the journal. And it is on page 10. So for $5 a piece, I will autograph it. It'll be worth money someday. So just to cheat ahead a little bit, I mentioned earlier that our mechanical room's behind glass. You can see that right here in the picture. So in our building, it's roughly a third of our building is office space, and then the other 2/3 is going to be manufacturing. So company, not to sell anything, but just so you know what we do, we manufacture VFDs in the building along with a lot of their power electronics. So keeping the environment clean is important, keeping a good level of humidity is important. Last thing I want to be doing is rubbing my feet on carpeting, going up and touching something electronic and giving it a shock. So not a good idea. So keeping humidity right at 30% in the middle of a Wisconsin winter is a very important thing to us. So a lot of guys think of, oh, HVAC, that's real critical for data centers so things don't overheat. Well, guys who are doing manufacturing would probably argue with you a little bit too, because they need to keep things just right to make sure you have high level quality in your product. So goals of the renovation, typical things. More reliable system. Example, we have a server room, and there was a dedicated air handler in there, and that unit was so unreliable that our rent-a-cop, our guard at the front of the building, he has a schedule that he'd go around and just walk around and check on things. One of his checkbox things he had to do was go over and look at a little thermostat in the server room to make sure the temperature was really 72 degrees in there and that the unit hadn't failed. So not an intelligent solution at all. Required somebody to walk right up to it and check it every couple hours just to make sure it was up and running. So I mentioned humidity earlier. We had individual humidifiers. Again, things would break down. You had to manually check on everything. Because you're building things in the US, you got to look at, okay, well, obviously our labor costs are not going to be able to compete with China, so what else can you do? You make a quality product, but at the end of the day, it's all about price, right? So you need to keep your overhead costs down. So with this renovation, we knew we could help save some of our energy costs, drive that down, also not have as many breakdowns of our HVAC equipment. And the company as a whole is always green. All big corporations nowadays are being greener, so there's almost want to call it a mandate to constantly reduce our energy consumption year over year in our different buildings. So with this renovation, we targeted LEED Silver. Also wanted a much more intelligent building. Again, I don't want the guard to have to walk over past our server room to figure out that everything is running okay in there, that the air handler didn't go down. And then what's unique about this is, okay, everybody's in a normal office building, I want things nice and comfortable. Well, we wanted the ability to make it 10 or 20 degrees in a certain room for research and development so they can do some testing in really cold weather situations, because the product can get shipped out to cold weather situations where it's 0 degrees outside. If you're going to test it, you'd rather test it in a real world atmosphere. So we have a room in our building that our HVAC system lets us bring in 100% outside air and can manually override things. So now in Wisconsin, when it's minus 10 degrees outside, I can get that room down to minus 10 if I really want. Again, why I have a hard time getting guys from the Vegas area to come up to Wisconsin in the middle of the winter. So a little overview of the building here. Don't worry about all the little boxes too much here. Basically, what you've got right here is all the office. So every one of these little boxes here is a different VAV zone. Manufacturing floor, shipping, some more offices. So one of the unique things about this building is, well, shoot, now I've got big old doors opening up. I got semi-trucks backing up as you're loading product to it, so now you got building static issues where you need to make sure you can keep a positive pressure in your building. Otherwise, I'm going to have all this infiltration from outside bringing in all that really warm summer air, humid air, or in the winter, the opposite, bringing in all that cold air. So you want to make sure that you always have good building static control. Otherwise, as soon as you open those doors, you can bring all that bad stuff from outside, untreated air comes straight in. There's 7 different air handlers in the building, 2 that feed the office, one's on a roof, this one's in the mechanical room, we'll see some pictures later, and then the remainder of the air handlers are up on the roof also. So part of what I want to talk about today is going to be a little bit of a HVAC 101 for when you have a system with a central plant for cooling. So I want to kind of follow the airflow through how an air handler works, and then all the different points of data that we're monitoring in that air handler and how we use that information. So this particular air handler right here is going to be one that's feeding our office. So you've got your air coming in from outside right here, and these are actual screenshots from our automation system that are up here. These aren't anything generic off the web, off the internet. This is our actual building. So I've got air coming in outside. I've got airflow monitoring stations right here, so I know how much air is actually coming in. And because I'm doing an outside air economizer, in the winter, I shut my chiller down 100%. I use outside air to do all of my cooling. And then same thing early morning in the summer when it's cool outside, I don't need to start my chiller. Just open up my outside air dampers and bring in outside air, and that's all my free cooling. Can't do that quite as much in Las Vegas as you can in Wisconsin. And then it also mixes with some return air, and there's filters. So there's, I think it's a MERV 8 and a MERV 13 filter. So basically your cheaper furnace filter, then your MERV 13 filter to get all the higher quality indoor air quality. Catches everything. We have a pressure sensor across that. So one of the things that learning in a new building is, okay, what does a dirty filter mean? So year one, we've got a maintenance contract. They're going to come in and change out the filters every couple months, so be it. Long term, what we're doing is this point right here tells me how much pressure drop is across that filter. We're trending in our building automation system. So I can keep track of how much of a pressure drop equals a really dirty filter. And then I can set alarms in my building automation system that says, hey, my pressure drop across this filter reached X. Set an alarm, tell somebody to go out there and change the filter. So right now, it's just maintenance contract with somebody. They just come out and change it every couple of months. But long term, that's a cost savings because now we only have to change out the filters when it's really necessary. And me being a VFD guy, I got into this about halfway into the project. I could have done something very similar looking at the torque setting of the VFD and trending torque information and use that to figure out when the filter was dirty. But because we've already got the sensor across there, might as well go ahead and use that. And then everybody likes pretty graphics, so that color on the graphics will actually change as the filter gets dirty. Then you're looking at your mixed air. So you've got your outside air and your return air. So you've got mixed air temperature right here. And here's your supply fan. This particular unit's a smaller one. I think it's 7.5 or 10 horsepower. The larger one's feeding the production floor are 30 horsepower supply fans. I think one of them's even a 40 horse. Got a VFD on here, obviously. So the VFD, what it's doing is it's looking at duct static pressure, and its goal is to maintain a specific static pressure. So in this particular example, it is a 1/2 inch, which is pretty low. So you're like, oh, that's low. Why are you so low? Well, one of the things we're looking at is having a reset of the duct static pressure. So I know it's kind of hard to see on here, but it says the maximum position of a VAV box is 73%. So if all of our VAV boxes are kind of pinched off, none of them are screaming and asking for air, there's no need to have a high duct static pressure. So we actually lower our set point for the air coming out of here. So that's another energy savings technique, is instead of always being at 1 inch or always being at 1 1/4 inches, we will lower that set point when we don't need that much pressure. So it's just those little tiny things that help you save energy over the long haul. You've got chilled water for your cooling. So I got a little bit of outside air, but really the way I'm doing is cooling. I've got my chiller running, I got my valve open 54%, and I'm cooling this air. And what you can't see too well here is my set point is 55 degrees, and the air coming out of there is 55 degrees. There are times where we have our chilled water and our hot water running at the same time. Anybody have a guess on why we would do that or when we would do that? Yep, dehumidification. So we over chill it, get as much water out of the air as possible, and then we may have to warm it back up again. So we might have been having it at 50 degrees here and warming it back up to 55 degrees there, exactly. Then obviously we're looking at if we're gonna have a freeze stat, so we need to make sure I'm not gonna be freezing any coils. And then again, another mixed air sensor. Down here are 3 different alarms. We've got freeze, smoke, and high static. So what I like about this is if my unit trips off because of a safety, I know exactly what safety it is before I send anybody up on the roof to figure it out. What happens way too often, our guys will run the safeties all in series with each other. So if one of the safeties opens up, okay, unit stops, we've got a problem. Now I have to figure out what safety it is. So I can be at home on my phone, I can look in here and say, oh, okay, it's the freeze went off. I can tell somebody to go out and specifically look at that and see what's going on. Opposed to saying, yeah, we've got a problem on the air handler's down, I don't know why, go out and fix it. So and then the other important part of what we did here is we didn't just run the safeties back to the building automation system, we ran the safeties back to the VFDs first. So that way, if somebody comes up and puts the VFD in hand mode, or puts a VFD in bypass mode, those safeties are all still in the circuit yet. I can't tell you how many times I've seen guys just run the safeties back to the automation controller, and then at some time the drive gets put in hand mode. That's how you blow out ductwork, because now you don't have your high static cutout in the circuit anymore. So you're like, well, geez, Tim, how do I know if it's a freeze, smoke, or high static cutout if you brought the safeties back to the VFD instead of the building automation system? Well, what we can do with the building automation system is I can monitor those 3 digital inputs on the drive through BACnet. So if I see one of those digital inputs activate, okay, now I know that particular safety just opened up, and over BACnet, the building automation system can show that on the graphics. So again, me being a VFD guy, one of my pet peeves are running the safeties in series and not running them to the VFD. So if you ever have any pull or stay in a new installation and you can fix that, please do. Tell them to make sure that they run the wires ahead of time for each individual safety and don't put everything in series. At the end here is the symbol for our humidification. These screenshots were from the summer, so in Wisconsin I don't run my humidification in the summertime. I'm only running it in the winter when it's dry. This would be a little bit different story down here. Then I've got return air coming back here. I'm either going to exhaust it for building static control. I'm looking at return air temperature. I'm looking at making sure there's no smoke in my airstream, make sure I don't need to trip the unit off. And then return air will come back up here and get mixed. And that's your typical air handler. Any questions on this? How many of you guys knew this like the back of your hand? A couple of you. Yeah, he recognized graphics, huh? For these type of classes, I have to go out of my way to make sure I don't have too many logos in there, but that is correct. One other thing I should mention also, down here, we also implemented demand control ventilation. So one of the things we had were CO2 sensors. So if I know what the CO2 content is in my space, there's no need for me to have to bring a certain amount of outside air in. If it's 90 degrees outside, I really don't want to bring that 90-degree air into my building. So if my CO2 levels are nice and low, I can completely shut off my outside air and just run 100% on return air along with my chiller running. So we did this in the office space. However, we did not do this in the production floor. Production, you're doing things like soldering, there's other things going into the air, so you still want that minimum amount of air turns going around in there. But in an office setting, there's nothing really bad in there, so all we're just doing is looking at CO2. CO2 levels get high, we start bringing in some outside air. We made that adjustable because this is one of those learning things. When you have a building, you never truly know what is the right number. So an ASHRAE standard is 1,000 parts per million, but you can also read articles where people will say if it's 600 ppm that it feels really stuffy. So basically we're just gonna kind of watch our residents, the folks who are in the office, and if they start complaining about being stuffy, I'm gonna start lowering my threshold for what's acceptable for parts per million for my demand control ventilation. For those of you who plan on downloading this presentation, after this you'll get an email as long as you scanned in, which will then give you the information on how to download this. Basically, I'll have a picture, and then the next slide talks about a lot of the high-level topics of things that are of interest. So just to make sure I didn't miss anything here. Oh, I should also mention that 55-degree temperature coming out of here, that will reset based on the space's requirement. So if none of the spaces need 55-degree air, if they're okay with 60-degree air and it still can cool it, we will just bump up that temperature. Again, whatever you can do to get more energy savings. And everything that you're seeing on here is all coming back via BACnet. This VFD for that supply fan right there is run off of a twisted pair. Start, stop, status of the safety is going back to automation system. Its speed reference is all coming from a twisted pair. Now I'll give you one of those little dirty little secrets of how things get installed versus how they should have been installed. The BACnet standard for an isolated device, which is what a VFD is, says you should be running 3 wires. Your A, your B, and a reference. They only pulled a twisted pair, shielded twisted pair for our building. However, because they follow good wiring practices, there aren't any problems, so I'm not going to make them rip a bunch of wire out. There's no need to if there's no problems. But that's just one of those things when you're running communication wires, really what you're supposed to be doing is pulling a twisted pair and then that third wire, which is your reference, plus, minus, and a reference. So right now I can see that VFD is running at 31 hertz. I can see how many kilowatts it's drawing. So long term, what I'm planning on doing is I'm going to bring all the VFD kilowatts out to a single screen, and I can use it as a pretty good estimate of how much energy my building is using that is dedicated to HVAC. Because most of my pumps, my fans are all on VFDs. The only big load I have that's not on a VFD is our chiller. And me being a VFD guy, I think we probably should have had the chiller on the VFD, but that was before I got involved. Right. You can definitely get a chiller with VFDs. That's becoming newer. 20 years ago, you didn't really see many VFDs on chillers, but it is something, one of the things we kind of look at is chiller retrofits, putting a VFD on a chiller. There's some expertise you need to have in the chiller before you just dive into that one, though. What's that? Yeah, using VFDs is becoming the norm. There's an ASHRAE standard, ASHRAE 90.1, for typical pumps and fans that actually says above a certain horsepower, you must use a VFD. I think don't quote me on this, but I think for a 5 horsepower fan and above, you have to use a VFD, and I think the pumps are like somewhere in that 7.5 to 10 horsepower range and above, thou shall use a VFD. And folks typically almost use ASHRAE 90.1 like a building code, so that's helping drive the use of VFDs. This particular screenshot here is of one of the units that's in our shipping and receiving area. It's very similar, except no humidification. I'm right by outside doors, so whatever I'm coming out of there for humidification is really not going to help that much compared to what's, as soon as I open this 10 or 12 foot tall door. So no humidification is there. But however, you'll see these down here. These are infrared heaters. So again, I'm in Wisconsin, so we've got the minus 20-degree weather because the polar vortex is hitting us again, and the poor guys are trying to load stuff on trucks. So we have the infrared heaters in there to turn on to help aid in the heating in addition to the warm air that would be coming out of the air handler. Again, all controlled via BACnet, so all serial communications. I can see all that information. Same thing for the exhaust fan. I can see exactly what my building static is. I can see if the drive is faulted or not. One thing they didn't do that I'm going to have them add on as part of a warranty stage of our project is there's no alarm that tells us the VFD has been put in hand mode. So I've seen times where somebody puts something in hand mode because they're testing something or it's not working, and then they walk away. Or they put it in bypass mode and then they walk away, and the motor's sitting there at 60 hertz all day long, 24/7, and there went all your energy savings you got for putting a drive on it because now it's running at full speed. So what you can monitor is a point in the drive via BACnet and actually have it alarm the system and say, hey, somebody has me in hand mode, or hey, somebody has me in bypass mode. I kind of quasi have that now because if the unit is running when it's not supposed to be, when it's supposed to be off, it will generate alarm today. But I'd much rather just immediately generate alarm in the building automation system whenever the drive. No demand controlled ventilation because I have trucks backing up to this, so I want to make sure I'm always having a decent amount of air flowing through this area. Also, once we get to the production floor, it's not a variable air volume space anymore. It's a single zone variable air volume almost, because we're just feeding one big zone, but we have a drive on it. So they've got some algorithms in there that can back up on the VFD speed when you don't need it. Again, more energy savings. I'm going to move over to the water side. Anybody have any questions on the air side before I do so? Eventually there will be somebody brave enough to raise their hand. So let me start with the chiller, because that's where everything really starts as far as trying to cool something. So chiller right there. And so whole deal with the chiller, half of it makes cold water. The other half is a side effect. One of those physics things is we need to create something hot if we're making something cold. So there's your condenser water, your warm water. So we'll talk about that later, and I'm going to ignore the ice storage initially. So we've got a chiller, makes our cold water. Right there it is. We're going for 43-degree water. We're at 46 at that moment. Comes through here and goes through this valve, goes out to all the different air handlers. Now, again, me being a VFD guy, I much rather would have put another pump and a VFD on here to control the pressure out here, opposed to putting a bypass valve in here, but it's the way it was installed, so be it. So as all those different air handlers, those 7 different air handlers we got, as they start calling for more and more chilled water, more and more will come through here. And you can see right at this moment, I took this screenshot, it was roughly a 9-degree temperature drop from the water going out to the air handler and the water coming back into the air handler. So water comes from the chiller, goes out to all their air handlers, which are all out over here that you can't see, comes back in 10-ish degrees warmer, comes through 1 or 2 of these chilled water pumps. So what we did is we designed our system as a redundant system. So only one of these 2 pumps will ever run, and every 100 hours, it will rotate between which pump is running. So each pump has a drive, and only one ever runs at a time. So redundancy, we didn't want our system to go down, we wanted something reliable. The other option, which you'll see a lot of times, is 1 pump and a drive with a bypass. So if the drive was to ever fail, you could just put it in bypass. But then if you had a problem with your pump, SOL, there's nothing you can do about it. So we designed ours as a redundant system, 2 pumps, 2 drives, rotates between the 2. Also, if one ever faults, the automation system will see that via BACnet, and they will go ahead and transfer over to the backup drive. So remember earlier when I was talking about the way it used to be, our security guy would be walking around with a checkbox thing and making sure things are working. Now it's smarter, now it's all automated. Automation system says, hey, I just saw a fault over BACnet of VFD number 1. I better switch over to VFD number 2. And maybe that VFD faulted not because of a VFD problem, maybe there's a short in the motor. So it caught that, tripped out to protect itself, but now we still need to pump water through the building for cooling. So that went to the second unit.
May I ask you a question very quick? Because you mentioned the secondary pump that you would recommend and
Yep.
the VFD and everything, especially on the chiller plant upgrade. So you go to the chiller plant, you have 2,000-ton chiller plant, and you want to, you do a major upgrade. So and a lot of times in discussion, should you mimic the existing system? So if you have just one loop, would you go with 2 loops, and eventually go back on the air handler hand, and if they had 3-way valves, go to 2-way valves? Have you had exposure to that kind of application, and what was your experience on, increasing the efficiency of your own overall operation?
I'm going to leave some of that more to the chiller guys because they'll have a little bit more real world experience. Generically, what I see people do is they try to keep things the way it used to be just because it's easier, it's less cost, it's less intrusive to try to change things. So they will try to leave it the way it was. My personal preference is I always like primary, secondary. See, to me, it gives me more control, more ability. That goes back to my initial statement from as far as the way I see it typically happen. They leave it as much as possible like the original way.
Maybe I didn't say the question right. So did you have any exposure where you were able, on project where you were able to track the energy efficiency improvement? Say, hey, it really makes sense. Look, I dropped from this to this, and on a similar building across the street, I just mimic the existing system, and the efficiency increased by this. I dropped the usage by only 20% versus 40% here. So at the end of the day, you make a point for yourself, say, hey, I'm proposing this option because look, it pays for itself, it has a payback of.
Yep.
But,
I understand your question just from a VFD point of view. I usually don't get to see the big picture a lot of times in the projects I'm involved in. I figure out, okay, this is the product that I can supply to make this work. And then somebody who gets paid a lot more than I do that has consulting engineer next to their job title will know those details. And water comes back up, chills to water, continue to loop. So, yeah, that's cool. Everybody's got a chiller in a big system. We wanted to do something better than that. So what we did is we added thermal storage. I got a big 9,000 gallon square box outside that we make ice in. So what we will do is during the evening time, off peak hours, so our building there's nobody left after about 11 o'clock p.m. We will have the chiller turn on, go down to about 20 degrees Fahrenheit, and instead of having that water loop go out through the rest of the building, we just have that loop come this way and it ignores the rest of the building. And what we're doing is we're making ice in here. So imagine a big tank with a whole bunch of metal pipes going back and forth. That's our glycol mixture, and we're bringing that glycol mixture down to 20 degrees, which then freezes all that water in that big ice storage. So now during the day, instead of running my chiller right away in the morning once it starts to warm up, I instead have my chiller off and I route my water through my ice storage tank. And now I use this big brick of ice to make the chilled water and cool my building. Any of you guys doing this today? This is something more in the future. So again, our building trying to be a cutting edge, we kind of talked to some of our more advanced customers who like to do things like this, and this is one of the things that they suggested that we look at. So that's what we implemented. So,
that's a good idea.
yep.
I was going to say, in order to drop your chiller down to 20 degrees, you're using something other than water, because now you're running a chance of blowing that chiller.
Exactly.
And I figured that you was using glycol.
Yep. And even just being in Wisconsin where I'm at, even if we weren't doing this, we would still be using glycol just because of the winters we have.
So basically, everything you have in the chilled water loop is glycol.
Correct.
Because that reduces the efficiency of you pump a lot more glycol or glycol mixture than you would pump water.
It's one of the side effects.
You're going to do a separate loop for the ice storage loop. But that's it, it's a design.
Yep.
We done the same thing, but instead of license, chilled water to 39 degrees to 200 gallon tank.
Okay. Cool.
Run at night. We did the same thing. Instead of making ice, we make 39 degree water in a 2 million gallon tank. And then we use the water
I was at a university in New Mexico that was doing the same concept. Different kind of thermal storage, same concept. To give you guys sizes, this chiller is only a 400-ton chiller, and this ice storage is about 750 tons of ice. So one of the things we do is and this is still learning your building because it's still a new project for us, is we keep track of how quickly we run out of ice. Because the last thing I want to do is run out of ice at noon and also have my peak energy being at 2 p.m. I want to make sure that my ice lasts. So one of the things we're playing around with a little bit is, okay, do we want to go 100% ice until the ice is completely gone? Or do I want to do a little bit of mix, maybe run my chiller only at 25%, and then get the rest of my cooling from the ice. So this is all part of the learning process. This isn't one of those things where you install it and your controls contractor walks away. This is a learning experience. If you truly want to optimize your system, you have to trend it, use your building automation system to its full advantage. So that's all the cold water side. Now I'm going to talk about the warm water side, because regular chiller system just wasn't good enough for us. We wanted to do something cool. Showcase. So here's our chiller again. This is going to be the warm water side. So first I'll do the normal stuff first. So you got your condenser water is coming out. And again, redundant pump system. Alternates based every 100 hours. We're going to change to the other one. One VFD per pump. So that way if either a pump or a VFD goes down, it'll auto transfer to the other one. And then there's a plate frame heat exchanger right here. And I'll explain why we needed that in a second. And I'm going to come to the other side of the picture here. So here's the other side of that plate frame heat exchanger. And now my water is going out to my cooling tower. So there's a VFD on this cooling tower. The PID loop for the VFD the control scheme for the VFD is inside the VFD. So the PID loop that controls how fast the fan should run is actually in the VFD. So they give us a temperature set point. The VFD will automatically ramp up or ramp down the fan as necessary to maintain that 95, that 100-degree water temperature. And you guys are like, oh, that's kind of warm. You don't want 95 or 100-degree condenser water. Well, we'll talk about that in a sec. Another cool thing we did is halfway through the project, I was like, you know what? I live in Wisconsin. We have times where it's really cold. Now it's warm. Then it's really cold in October. We don't really know when we truly want to have our cooling tower completely drained. We did a auto drain feature. So now if it's cold out for below a certain temperature for so many days in a row, we will automatically open up these valves and it will dump the cooling tower. And then if it's warm for so many days in a row and we have a demand to have our chiller running again, we will autofill our cooling tower. So because this is one of those adders that we thought of after the fact, and any good controls company just says, ooh, I can make money on adders, I can sell you a NEMA 3R controller that I put out on the side of that cooling tower to control all those valves for you. And we're like, well, shoot, we got a VFD on the side of here, and we have relay outputs that are available. So what we ended up doing is having the controls contractor write some code that they send over BACnet to our VFD that tells the VFD when to fire its relay. So there's relays on there, pass-through I/O, that they can control. They're basically extra DOs, but they're stealing them from my drive opposed to their controller. So now they didn't have to get an extra controller. They just used the logic from an existing controller over BACnet to my VFD, and then the VFD was able to open up those valves. Why cooling tower opposed to putting the chiller out on the roof? It's part of the showcase aspect of it, is we wanted to have a more advanced system. So that's what these guys are down here. Again, everything's over BACnet, so I can see if the drive is started to stop. They can see the status of it. The cool thing about the PID loop being handled in the VFD for the cooling fan is if for some reason that communication was lost, it'll just remember the last temperature set point that was given and modulate the fan up and down as necessary. So now I'm going to flip over, go back a little bit. And you're like, well, what the heck are these pipes right here coming off of here? This is a heat recovery chiller. So what we said is, well, we've got warm water coming out of this chiller as a side effect, condenser water. Let's take advantage of this. So we actually pipe our condenser water into our hot water system. So we can use that for all of our VAV reheats during the summer. So during the summer, I don't run my boilers. Boilers are completely off. It's pretty good when it vibrates on there. It's impressive. So another energy savings thing, during the summer, no natural gas boilers, just using condenser water. So that's why you have to have a special type of chiller to do this, because my condenser water is usually between 95 and 100 degrees Fahrenheit. So because it's higher condenser water, you may need to have a chiller that's designed for that higher temperature. And to show you some of that goes on when you're designing a system, we had one control signal telling the VFD to have 75 degree temperature. We had another control signal that was saying 95 degrees, and they were fighting each other. And I'm walking into work one day and I can hear the cooling tower fan going like just faster, slower, faster, slower, faster, slower. So those are just little things you find as you're going through a project that need to get fixed. And the reason we have this plate frame heat exchanger is all those chemicals that you have in your cooling tower, we don't want those getting into our hot water loop. So that's why we put this plate frame heat exchanger here to isolate that. So on the hot water side, we have two boilers, natural gas high efficiency boilers. Now they're talking different communication protocol, Modbus, between the two of them, and they're figuring out what's more efficient. Do I want to run one boiler at 75% fire, or do I want to run two boilers at 35%? So they're constantly talking to each other. That's part of the boiler feature. That's not what the automation system is doing. That's just a characteristic of the boilers to figure out what the most optimum energy efficiency point is going to be. So that's during the winter time when we need to do the warming. And then again, we have redundant, our hot water pumps. One runs, one does not run. Every 100 hours they cycle. If one faults, it'll swap over the other one. That's all possible because of BACnet and the building automation system. Non-HVAC things that we're doing, I'm looking at on the right, this one right here is a graph of our power factor. So we can either get a rebate from our power company if we have really good power factor, or we can get a penalty because of negative power factor. So I can graph, I have a communication link out to my We Energy's power meter. So on my operator workstation, I can look at the power factor of our building in real time and I can trend it. So now I can go out to the manufacturing floor guys and say, you know what did you guys do right here that made my power factor suck? Because we have to pay a penalty because you did this. What can we do for staging wise to fix that? Same concept here. I'm looking at our instantaneous kilowatt from that our building is using. So to give you an idea, this is a day 1, day 2, day 3, day 4. So during the afternoon, nighttime not occupied. During the afternoon, nighttime not occupied. This might have been a weekend or day that maybe we weren't doing as much work. So having all this information at my fingertips just makes the building so much more flexible because I know exactly what's going on in real time and I can compensate and make adjustments based on that. So yeah, instantaneous kilowatt, nothing to do with HVAC. Oh, wait, we've got ice storage and I want to make sure that I'm using my ice at the peak of these to try to flat top these peaks, get my energy costs down. So it all ties in together. It's not just HVAC, you're bringing in other information also. And this is where it comes to having that smart building. So different pictures, there's a chiller, lineup of VFDs there. We've got our boilers back there. Your orange are going to be your condenser water, your chilled water, and your hot water. Another angle, this happens to be a fan wall style air handler. Unfortunately, we didn't have enough room in our area to make this as long as we needed to, so my humidification is up in the ceiling and the ductwork right outside this room, but normally the humidification would be the final stage in the air handler. That panel right there is the panel for our humidification, so we don't use steam, we don't use natural gas boilers to get our humidification. We actually use pressurized water, and that cuts down the cost significantly from an energy consumption standpoint. Lineup of VFDs. Whenever I see a VFD, I come up looking for three things, 3 conduit runs: input power, output power controls. If I don't see 3 conduit runs, either they're not having any controls coming into it, or somebody screwed something up. There should always be 3 conduit runs. I don't want high voltage and low voltage mixed together.
Or is installed right on the equipment, so you have just conduit in, control, and you run right there on the motor?
If it's right, there still should be some degree of conduit run from the drive to where the motor's at. There was one that caught me off guard the other day. I was at a customer, and the drive was mounted right on the air handler, and they had brought the conduit in straight in the back. So I only saw the 2 runs. I'm like, okay, what did you guys do? And I had to kind of get back around to see where that 3rd conduit run had came. Cooling tower outside, along with that right there is our ice storage. So that's our 750 tons worth of big old ice brick. So just a general recap for guys who aren't just familiar with the systems. You got your chiller, makes chilled water that your air handlers then use to cool the building. You've got a side effect of your condenser water. We happen to use that to help with reheating in certain parts of the building. So if a VAV box, if we don't want 55-degree air coming out of here, maybe we want 60-degree air, there'll actually be coils up in a VAV box that'll warm up the air a little bit. A couple natural gas boilers that talk to each other to be efficient. We got an air handler. As I mentioned, these are hot water or cold water to do the cooling. So that's it for the HVAC side. I'm going to spend a little bit of time talking about VFDs and BACnet because those topics came up time after time after time in there. So if you have any questions on VFDs, feel free to throw them out there. You can also stop by our booth if you want to go into more detail. So the who, what, where, when, and why, and how of VFDs. The when is, when do you use them? Well, all the time as far as I'm concerned, and I'll talk about why. So what are VFDs? We control the voltage and the frequency going out to the motor to control how fast the motor spins. It's that simple. Whole crap load of names: speed drives, freak drives, variable frequency drives, adjustable frequency drives. There's literally like 10 different names that people will call a drive. Thing on the wall I hope I never have to worry about. That's a common one that I hear referred to a drive. Basically what a drive does is it takes AC in, converts it to DC, and it manipulates that DC into an AC-like waveform going out to the motor. So that's why they call it an inverter, is you're taking DC, turning it into AC. If you go down to Walmart and buy one of those things that you can plug into your cigarette lighter in your car that turns it into 120 volts, that's an inverter. It's taking DC, converts it into AC. So why are VFDs used? They're used to control flow. When they design this room, they look at, okay, what's the hottest temperature of the year? Okay, we're not going to design it for that, but maybe the second hottest. What's the max occupancy of this room? Okay, we need to basically be able to cover and cool this room for that scenario. So 99% of the time, that's not the case. So VFDs are used to back off on that flow. So earlier, we gave examples of duct static. So as VAVs are starting to back off, the fan can slow down. Use the VFD to slow down that fan. All about energy savings. The other cool part about it is you get a lot of maintenance savings aspect. Anybody ever walk by an air handler and when it kicks on or a pump and all of a sudden air handler, you hear a belt squealing? Well, that's because it's just bam, right across the line. You put a VFD on there, you soft ramp that up, it's going to last a lot longer. You're not going to be wearing out that belt nearly as fast.
May I ask you a question?
Sure.
You see, you talked about the start. How about the stop? Because I don't like, sharp
Yep.
stops on things. I have a 1,000-pound chiller. It's a drain chiller. It has VFD, and it screws up the combined heat and power plant generator operation because I dropped almost 500 kW in an instant, and I requested train to go back and give us an option to operate the chiller to slow down gradually to take off kW of the power distribution system gradually, and apparently they have a problem with that.
You can do a soft start. You can also do a soft stop. The only issue you run into with soft stops if you're trying to stop it too quickly, which is not the case in your situation, but if you try to stop something too quickly, I got a big high inertia fan that I want to stop real quick, the motor acts like a generator and puts power back to the drive, which could cause the drive to trip out, but in your case, that doesn't sound like that's the situation. So if there's a VFD on there, I don't see why, from a VFD's point of view, why that wouldn't work just fine, unless there's something mechanical else in the system where they want it to stop quickly. Usually HVAC applications, fans, I just say coast to a stop. Any pumps, tell my startup guys to ramp that to a stop, so that way you don't get that water hammer effect. That's something I see missed quite often, is guys don't set the pumps up to ramp to a stop, they just stop.
And that's all he would do there, is he'd program it to ramp to a stop with a delay.
That's what it sounds like. And you can choose 30 seconds, 120 seconds, however long you want it to be.
The only time it's gonna hurt you is if you have a sudden power outage. Then it just says, well, guess what, it ain't gonna matter, I'm done.
Medium voltage distribution, two outages in 10 years, so I guess we can take that twice in 10 years, but another one of the decrease.
But it can be programmed.
Just a graphical picture when we're talking about energy savings. The blue lines flow, so if I'm at half speed, I'm at half flow, makes sense. This line right here, that's horsepower consumption. This is something called the affinity curves. If I'm at 30% speed, I'm at 12.5% power. I mean, just a rule of thumb is you reduce the speed of a motor when you're using a VFD, you cut energy consumption by 25%. And this isn't the perfect curve because there's some inefficiencies in the motor. As you slow it down, it's not quite as efficient. But I mean, when I first saw this and started learning about VFDs, this was the wow factor. I'm like, why the heck are people not using these everywhere? An example on a payback, I did a 20 horsepower unit that runs 12 hours a day, 7 days a week. And in a unit that previously just had an outlet damper, it paid for itself in about a year. If it had inlet guide vanes, ignoring the maintenance aspect of that solution, it's a 1.5 year payback. Typical payback on a VFD is a 1 to 2 year range. And what I used for I used an ASHRAE bell curve for what your typical flow rate is in a VAV system. All common applications we're gonna see VFDs. In my hotel this morning when I was taking my shower, I'm sure a whole bunch of other people were taking a shower at the same time, so getting up the water up to the 34th floor, you need that booster pump really, really flying, but 2 a.m., not everybody's taking a shower, so there's no need to have that booster pump running nearly as hard. And then the last thing I want to touch on is BACnet, since I kept throwing that out there. That's a serial communication protocol that allows all different kind of devices to talk on the same wire. So I can take multiple different brands of devices. I mean, I can have an ABB drive, a brand X drive, and a brand Z drive all in the same wire, and the building automation system can talk to them all over BACnet. It's standard on a lot of products today. On a lot of HVAC drives, it's built in. There's no dollar adder to it. It's just standard. It's there. Use it. It's free. Well, hardware-wise, it's free. Still have to pay a controls contract to run some wire and all that fun stuff. There are over 100 points of information I can pull from a VFD and over BACnet. If you can think of it, we can pull from it. And then last slide I want to talk about is going back to our initial goals of this renovation we did our building. I can just rephrase that. A more intelligent building using BACnet led us to a more reliable system, something that reduced our energy costs, made our building greener, and we had that flexibility for that R&D guys so I can bring in that 20-degree air in the winter to do some testing. What other kind of questions do we have?
For your room that you want to have extreme temperatures in, we're fixing to do the same thing in the place where I'm at. Do you have any difficulties with the humidity swings?
We had to make sure that our folks who were testing the equipment understood that the humidity that was outside was going to be the humidity inside that room. As far as having the swing from high humidity to low humidity, I'm not aware of any problems there. I don't think we've ever we're going to be going from completely cold to warming it up immediately either.
That's kind of what ours, the training room does for extreme temperatures, and it can go from 1 hour to the next from 20 below zero to 110 degrees in an hour. I'm worried about if you had any issues.
I don't have any answer for you on that one. It's going to be a bit of a learning curve to see exactly what happens and then deal with it as it approaches.
Kind of what my people are telling me the same thing. They can't figure it out as it goes along.
Yeah. Last thing I want is a room that's all full of condensation.
I have a question. You mentioned at some point a few minutes ago about the efficiency increase on fans when you install VFDs.
what I like to do is have a guy, and I'll temporarily put something in hand mode, and I will ramp it up, because on the keypad of our drive, the bottom line shows us how many amps middle line is showing us how many amps the motor's drawing. I will show them the amp draw at 60 hertz, and I'll back it down to 30 hertz, and they think something is wrong because that number is so small at 30 hertz. So I don't have it written up, because every single person who ever goes into the mechanical room and actually tries that, they will see it real life. As far as motors, most motors today can actually be used with drives. They've started changing the design of them to make them more flexible for use for drives. So they've changed the insulation rating on them. So for the most part, the standard motor will still work with the drive. If you're doing a retrofit, we have to be 20-year-old motor. We got to be careful with things like cable distance and making sure we don't slow things down too much. The nice thing about a variable torque load is that light load, there's less torque, less amps, so it's less likely to burn up. So I'm gonna wrap it up here and hand it over to the next group. We're in aisle 400, so if you want to come back and hit me with some more VFD questions, I love it. I'm just a big drive dork, so I will answer as many questions I possibly can for you, and I'm pretty darn dangerous when it comes to HVAC.